Assalamu alaikum wa rahmatullah. Welcome back. This is Dr. Muhammad Saad, and we are continuing our lectures on computer communications and networks. In this video, we start with a new chapter, the network layer. In the previous lectures and videos, we covered the introduction. So we talked about the introduction chapter and introduction to this course. We talked about the data link layer chapter, and we talked about the medium access control or MAC sublayer chapter. And today in this video, we start with the network layer. In the OSI reference model, in the Open Systems Interconnection reference model, the network layer is the third layer from the bottom. So layer 1 is the physical layer, layer 2 is the data link layer, and layer 3 is the network layer. As we know from the introduction, the main task of the network layer is to move the packet from the source all the way to the destination. How can this packet be guided from its source machine to the destination machine, possibly making multiple hops along the way? So possibly going through multiple devices or from router to router until the packet arrives at the destination. And this end-to-end task, as you notice, the network layer has an end-to-end task moving the packet from the source machine, from the source host machine to the destination host machine, going through intermediate routers on the way. This is an end-to-end task, and this contrasts strongly with the main function of the data link layer that we have just finished. The main function of the data link layer is to move the packet, is to get the packet transmitted along a link from a device to the next device going through one link. So the scope of the data link layer is the transmission over a single hop, and the scope of the network layer is to get the packet transmitted basically or routed from the end host to the other end host, from the source to the destination. Now, to summarize the different functions of the network layer, and this agrees with what we have said in the introduction, we say routing, congestion control, internetworking, in short. Let's elaborate a little bit more. Routing means the routers in the network will work together to understand the network topology and to find the best path basically from the source to the destination so that packets can follow this path, and this is what we call routing. Congestion control means avoiding to congest parts of the network. Let's say, let's make sure that the packets will not all go through the same link so that the link becomes oversubscribed, it becomes congested, which means future packets can get lost. Excessive delays, which basically negatively affects the quality of service. So avoiding congestion, and also dealing with the case or dealing with the situation when the source and destination are on different networks. They're not basically connected to the same network, and this is what we call internetworking. And in this chapter, we will basically talk about most of these issues. Also, as a reminder before we continue, let's remember the meaning of the store and forward packet switched network. So we have basically a host machine at the edge of the network. So this is host 1, which represents a user's device like our desktops or laptops or phones and so on. Host number 2, another user equipment. So on the outside of the network, we have the user's equipment, we have the hosts, and in the core of the network, we have basically the carrier's equipment. So at the edge, we have the hosts, which represent the customer's equipment, our own devices, our own computers, desktops, laptops, phones, and other devices that are connected to the internet, right? And the purpose of these devices is to run applications that exchange messages amongst themselves, right? And we also know that inside, in the core of the network, we talk about the carrier's equipment. So the equipment that belong to the companies that implement the internet, that implement the network. And these equipment are basically routers interconnected by high-speed communication links. So routers and links that provide the connectivity, and we have customers' equipment hosts that use the network. Right? Now, how do these routers operate? They use the store and forward principle. So if a packet arrives, host number 1 sends a packet here. Host 1 sends a packet. By default, due to the connection here, host 1 will send the packet to router A. Router A will investigate the header of the packet, and then it will decide to forward the packet either to B or to C, depending on what is the destination and basically what is the best path towards this destination. Now, to get this accomplished, router A needs to store the packet in a buffer, until this packet is processed by reading the header, checking the destination address, and then deciding which way it will forward, and then only then the router will forward the packet. So we have two things that happen in the router. The packet is stored in a buffer, of course processed, and then a forwarding decision is made. The packet is forwarded along the next outgoing link, going to the next router, which will repeat the operation until the packet arrives at its intended destination. So here in this slide, we just reviewed the store and forward principle. We talked about this in the introduction. And we also defined the different networking equipment here. We simply distinguish between carriers equipment that belongs to the basically the companies that implement the network, routers and interconnecting links, and the customer's equipment, our own desktops, laptops, phones, and other devices that are connected to the network. Now, this store and forward operation, again, the router stores a packet and then does processing by reading the header, checking the destination address, and then deciding on an outgoing link. How is this operation done exactly? In other words, how is the service provided by the network layer done? We know that the layers are designed in such a way so that each layer provides a service to the layer on top. We know that the network layer is layer 3, and layer 4 on top of the network layer is the transport layer. So as a basic principle, we know that the network layer provides a service to the transport layer, and this service is simply guiding the packet until it arrives at the destination, because the transport layer is basically responsible for the end hosts. So the transport layer would like to get a message delivered from host 1 to host 2, and this basically is implemented by the network layer by finding suitable paths so that the packet can follow this path. In short, we would like to remind you of how this service, basically, the service which is provided by the network layer to the transport layer, how can this service be implemented? And we have two different services, basically. We have two different types, a connectionless service and a connection-oriented service. Connectionless service means the following. If host number 1 has a message that needs to be sent, if this message is large, the message will be divided into smaller packets. Each packet will have a header that carries the full address of the source, the full address of the destination, and then the packet will be injected into the network. Bottom line, different packets get basically injected into the network independently. They get routed in the network independently. It is possible that different packets that belong to the same message take different paths in the network. So here, packet number 1 may go this way, packet number 2 may take another path or another route, depending on the network conditions. So we have no advanced setup. We don't have, in connectionless services, we don't have the notion of choosing a path and fixing it or reserving it. Packets are injected into the network individually and routed independently. Packets in this context, so in this context, as long as our subnet provides a connectionless service, in this context, packets are also called datagrams. So what is a datagram? It is just the name of the packet in case packets are delivered according to a connectionless service. The subnet itself, so the network or subnet itself, may be called a datagram subnet. Now what's the opposite? What's the other alternative service? It's a connection-oriented service. In the connection-oriented service, imagine that host number 1 has a message that needs to be delivered. Again, as usual, let's make the nice assumption that this message is large. It's like an email that has a large attachment. So we have a message of a large size, and this message needs to be divided into smaller packets. Now, how will these packets be delivered in a connection-oriented service? Before sending any one of these packets, a path needs to be chosen from source to destination. An end-to-end path needs to be chosen from source to destination. This path will be dedicated for these packets, so all packets will follow basically the same path. So a path from source to destination needs to be established before any packet is sent. This path, in the context of connection-oriented service, this path is called a virtual circuit. A virtual circuit. And then the network itself, or the subnet that operates in this way, is often also called the virtual circuit subnet. So what is a datagram? It is the name of the packet itself in case packets are delivered in a connectionless way, right? And What is a virtual circuit? It is the name of the end-to-end connection or the name of the end-to-end path if basically we are using a connection-oriented approach to deliver packets. So connectionless versus connection-oriented. Now, in the following slides, we would like to talk a little bit more about the details of how these two services are accomplished and what are the tables involved. You will see that in both cases, routers are maintaining internal tables that help them make a forwarding decision, that help them decide whenever a router receives a packet. Using those tables, the router will decide how or along which direction this packet is forwarded, whether we're talking about a connectionless service or a connection-oriented service, and let's learn about that. So let's start with the connectionless service. For simplicity, let's assume that host 1 has a sequence of packets that need to be sent to host 2, right? Packet 1, packet 2, packet 3, packet 4, and so on. Connectionless means each one of these packets has a header which contains the full address of the source and the full address of the destination, and then these packets will be injected into the network one by one individually. And then whenever a router sees one of these packets, it will make an individual decision how to forward these packets. So bottom line, and this is also the end of the story once we talk about these tables, as you notice here, packet 1, 2, 3 are all following this path from host 1 to host 2, are all following the path from router A to router C to router E to router F, and then finally to the destination host. And packet 4 will take an alternative path because it is assumed at the time when packet 4 was sent into the network conditions have changed, so router A will decide to send it along an alternative path. Now, how are these decisions made? These decisions are simply made by having these routers maintain tables that we call routing tables. So how does the routing table look like in case we have a connectionless service, in case we have a datagram service? It looks as follows. It is simply a table with two columns. So what you see here is an example table at router A. So this could be the table maintained by router A. What you see here could be the table maintained by router C, and this could be the table maintained by router E. By the way, in this part of the video, in this part of the lectures, we just focus on the structure of these tables. How do these tables look like? What is their structure? And how are the routers using these tables to decide how to forward the packets? So this is an issue. How are these tables being used by the routers so that the routers decide how to forward the packets? However, it is a totally different issue of how these routers come up with these tables. Why is it this table and not another one? How do the routers come up with the information in these tables? This is a separate issue, and this is basically related to the routing algorithm which is implemented by the routers, because simply speaking, these tables reflect the best paths from the router, the owner of the table, to every possible destination in the network. So currently, in this part of the video, or in this video itself, we just focus on the structure of the table and how it is being used by the router. So again, in the connectionless case, the table has two columns, simply two columns. The first column is the destination column, and the second column is the next hop column. So here we have destination, and in the other column we have the next hop. Destination means all possible destinations in the network. You know, destinations are basically hosts. Final destinations are really hosts. But to reach that destination, usually we reach a router. Imagine that we want to send something that needs to go to host number 2. Right? So it means that this packet will have to reach router F first, and then in the final stage, that packet will have to go through a local network going to the destination host. So for simplicity, we can assume that the destinations are every possible router in the network. Every possible router in the network. So if we're talking about the routing table for router A, what is the set of every possible destination? It is the other routers in the network, so router B, C, D, E, and F. B, C, D, E, and F, all possible destinations. Now, what about the next hop column? The next hop column indicates what is the next hop towards this destination. Let's dig in and look at an example. If this here, what you see here initially, I did not talk about this table yet. I'm talking about this initial table of router A, and we're having two columns, destination versus next hop. Of course, this is the table that belongs to A itself. So since this is the table that belongs to A itself, A as a destination is irrelevant because I'm A myself, right? If I have a packet that wants to come to me, it means I have it already and I don't have to forward it anyway. So A as a destination is irrelevant. That's why we don't have a next hop, because it means I have this packet already. Now, according to this table, if A receives a packet and this packet wants to go to destination B, according to the table, the router needs to forward to B itself, right? If the destination is C, according to the table, router A needs to forward to C itself. Now, if the destination is D, if A receives a packet and this packet needs to go to destination D, then according to the table, the router A needs to forward the packet to router B. So if I want to send something to D, according to this table, I have to forward to B, right? If I need to send something to E, so if E is my final destination, according to this table, I have to send to C, right? And if F is the final destination, then according to this table, I have to send to C. So again, on the left column, we have all possible destinations. Of course, the only one that's not relevant is the owner of the table itself. And then in addition to this, we have every other router in the network that pretty much represent every other destination in the network. Now, in the second column, we have basically, we indicate what is the next hop, what is the next router. Again, what is the next router I need to forward the packet to so that the packet will arrive at this destination? What is the preferred next hop basically towards this destination? As you notice, the next hop is definitely one of the router's neighbors, right? So if this is router A, according to this network configuration, according to the network topology, the only neighbors, direct neighbors of router A are B and C. So if A needs to send to any destination in the network, the next hop is definitely among B and C. As you notice, B, C, C, and so on. It is one of them. The only question, which one is better for every destination? So that's the meaning of this table. Let's have a look at the table for C. So router C has a similar table. In the left column, we have the set of all possible destinations, A, B, C, D, E, and F. Of course, C is the one which is not relevant because this is the table for C. So this is the left column, all possible destinations. And in the right column, we have the next hop, the preferred next hop towards each one of these destinations. So as long as we focus on this table, right? As long as we focus on this table says the following. At router C, if the destination is A, the next hop is also A. So if you receive a packet that wants to go to A as a final destination, send to A directly. This is what the table says. If C receives a packet that wants to go to B, it needs to send to A as well, which means anything that goes to B has to go this way. This is the preferred next hop. Now, C is not a valid destination because C is the router itself that owns the table. And here, if the destination is D, the table suggests to send to D directly. If the destination is E, the table suggests to send to E directly. And if the destination is F, the table suggests to send to E. So basically, if C receives a packet and this packet wants to go to destination F, according to the table, yes, I have a packet now, and that packet, yes, I know it wants to go to F, but according to my table, I'm talking about C's table. According to my table, I have to forward to the next hop, which is E, and then E will take it from there. So if the packet arrives at E, E has a table itself as well. E has a table itself, which contains all possible destinations versus the preferred next hop towards the destination. So instead of talking about each one, let me focus on one case. So imagine E receives a packet, and that packet wants to go to destination B. E receives a packet, and this packet wants to go to router B as a destination according to the table. In this case, the router E needs to forward to router D. So the next hop would be D. So basically, if E receives a packet that wants to go to destination B, it knows I have to forward to D first, and then D will take it from there. Now let's follow a packet so that we understand the full picture. So imagine host number 1 has generated a packet because the application has generated a message, and this message got divided into smaller packets. Each packet has the full source address and the full destination address, right? And then this packet will get injected, and from the configuration, as you notice here, host 1 is connected to the network through a direct link. So any packet that host 1 sends will go to router A by default. Host 2, just to show you another possibility of getting connected to a bigger network, that could be through a LAN as well. So host 2 typically could be like a computer on campus or in a corporation, in a company or so, and these computers are connected to the rest of the internet through a local area network, right? Again, let's go back to host 1. Host 1 has a packet, and this packet will get injected into the network. Obviously, it goes to router A. Router A will check the destination of the packet, and from the destination address, A will know that this packet wants to go to F because the final destination is host number 2. So A will understand that it needs to forward this packet to router F. So what will it do? It will check its own routing table. It will look for the destination in the table. Okay, if the destination is F, according to my table, I have to forward to C. So according to the table, I will not forward to B. No, I will forward to C. So the packet will be forwarded. It will go to C. What will C do? Once C receives the packet, of course, the packet will be stored. And then one by one, packet by packet, in turn, packets will be taken from the buffers, and then the headers are examined. The header of the packet is examined, and then from the destination address, C will know that this packet wants to go to F, and then from the other column of the table, from the next top column, router C will understand that it needs to forward the packet to router E. So from the table, if the destination is F, and this is in the header of the packet, if the destination is F, I have to forward to router E, right? So through the table, router C knows that it needs to send to E. For example, not to D and not back to A, right? So I have to forward to E. Now, when E receives the packet, it will consult its own table. E will also examine the header of the packet after storing, so store and forward. So in the processing phase, router E will check the header of the packet, and then from the destination address, E will understand it has to send to router F, and according to the table, if the destination is F, the next hop is F itself, so I have to forward to F. F, as you see in this configuration, in this topology, it's the final router, and then the last step going to the host is just through the local area network, right? So there is really no routing involved, there is no other router involved, right? So that's how it works. In the connectionless service, that's the structure of the table. Simply, we have two columns. In the left column, we have all possible destinations. In the right column, we have the next hop, the preferred next hop towards the destination, okay? How large is this table, by the way, so that we get prepared to the final comparison between connection-oriented and connectionless? How large does this table get? How many entries do we have in this table? How many rows do we have in this table? We have one row for every destination, so pretty much we have one entry for every router in the network, right? So when does the table grow larger? If the network itself grows larger, if we have a new router in the network, then the table will get larger, right? So this is basically a characteristic of the table that we use in the connectionless service. Now let's go to, this was the discussion that we have described here on the figure, and we go to the second case, which is the connection-oriented service. The connection-oriented service, in the connection-oriented service, as you will notice in this example and in another example that I've introduced here to illustrate the idea even more, right? In these examples, you will see that routers use tables as well, right? In connection-oriented services or in virtual circuits. In virtual circuits, routers use tables as well, but the table does not have the same structure as in connectionless. At the end, once we finish this, we have a global comparison between connectionless and connection-oriented, and this will be the conclusion of this video. Now, let's go back to this example. Here again, we have the core of the network that consists of routers A, B, C, D, and E, and F, right? And we have At the edge of the network, we have some user hosts, host 1, host 2, and host 3. And we assume that host 1 wants to send some packets to host 2. So host 1 has a message. The application at host 1 has generated a message, and this message is too large. It got divided into smaller packets. Now all of these packets need to be sent from host 1 to host 2. In the connection-oriented service, what do we do first before we send the packets, as opposed to connectionless, in which we're just sending these packets individually, right? It is possible. What we missed here, actually, it is good that we came back to this figure, to this slide. What we forgot to mention is what happens with packet number 4, right? We mentioned the following. Each router has a routing table. So this is the table at A, this is the table at C, this is the table at E. F is the router. It also has a similar table, right? Now, question. Once the router has a table like that, will it stay in use forever? Is the router using this table forever? No. As a matter of fact, these tables are updated periodically, typically every 30 seconds or so in the internet. The routers will communicate amongst themselves, and they are seeking information from each other so that they work on a routing algorithm, and eventually this table is updated to reflect the updated network situation. The details of this will come in future videos and future lectures, but for now, as you see here, let's assume that router A initially had this table, and then later the table has changed. So router A got involved in the update of this table. Somehow it updated the table with a new table. Now, when packet 4 got injected by host number 1 into the network, router A already had updated its table. So this is the table in use by router A at that time, right? What's the difference between these two tables? As you notice here, in this table that got updated, which replaced the initial table, right? At any given time, the router is having one table to be used. This was the table that was in use by router A when it was forwarding packets 1, 2, and 3. At the time of forwarding packet 4, the initial table was replaced by another table. So this is the table, this is the routing table actually being used. Now, if router A receives packet 4, again, packet 4 has a header which contains the destination address, and the destination address corresponds to router F. Now, when router A checks the table, it says, okay, if the destination is F, the next hop is B, and this is what has been changed. So perhaps router A noticed that this link became congested, the delay on this link became too long. Somehow it realized that sending along this way is better at that time. This got better, and this got reflected in the table. So from the table, router A will decide to send to router B. That's why packet 4 is going this way. So this is just the final comment here that we missed in the connectionless service, and we go back to our connection-oriented service. Now we have the following setup. Host number 1 has a sequence of packets that need to be sent to host number 2. So basically what happens is that host number 1 will establish a connection, will establish a virtual circuit between itself, host 1, and the final destination, host 2. As an example here, it is this red path that has been chosen. Of course, choosing the path itself is a big issue, and in the next lecture we will be talking about that explicitly. But for the purpose of this lecture, let's assume that somehow a good path is being chosen. Let's say the shortest path, or the path with the minimum delay, and so on. So a path needs to be chosen from the sending host to the receiving host, from the source host to the destination host, and this path is illustrated in red here. So as you notice, the path goes from host 1 to router A to C to E to F, and then finally to host 2. So this is the path that has been selected for the connection between host 1 and host 2. Host 1, A, C, E, F, host 2. The path needs to be chosen first and fixed, right? So imagine that this connection is being established first. So the other blue connection does not exist yet, because these connections basically are established one by one. Whenever a connection is needed, a connection is established. As long as it is still there, it is not disabled yet. Maybe we have another connection that comes on top of it, and so on. Now, so we choose a path from source to destination. In this example, as we mentioned, assume that this path goes from host 1 to A to C to E to F, and then to host 2. Look at the following. What are the routers along this path? Of course, host 1 and host 2 are hosts, and then the router along the path are A, C, E, and F. Now, how will these routers in the future, when they receive packets from host 1, as long as these packets belong to this particular connection, how will the routers know that they are part of this connection? How will they know what they need to be doing? That's why each router, A, C, E, and F, each router along the path, along the virtual circuit, will need to get a table entry, which basically identifies the router as being part of this virtual circuit. Let's look at these tables basically. This represents the table at router A. What you see here represents the table at router C, and what you see here represents the table at router E, and then router F will have a similar table as well, which is not shown in this figure. So router A has a table. In the connection-oriented service or in virtual circuits, a table always has two parts. It has an incoming part and it has an outgoing part, an incoming component and an outgoing component. What do we have in the incoming component? By the way, I'm talking only about the first entry here because it is the first entry that corresponds to this virtual circuit. And as you have noticed in connection-oriented services, whenever we need to establish a virtual circuit, in other words, whenever we need to establish a connection between two end hosts, we need to get a special table entry in every router along this path, right? Or along the virtual circuit. So the incoming component again has two pieces of information: the incoming device and the incoming virtual circuit identifier or connection identifier. How can we distinguish virtual circuits from other virtual circuits? How can we distinguish between this red virtual circuit from the blue virtual circuit? At the time when the blue virtual circuit is established, we will have both virtual circuits. How can we distinguish between them? How can we make sure that router A will not be basically confused between these two virtual circuits? By using something called the virtual circuit identifier. Let's cut the long story short. What is this virtual circuit identifier or connection identifier? It's a number. It's a numeric. It's a number basically that needs to be assigned along the virtual circuit. It is not a number for the whole virtual circuit. It is a number on every link for which the virtual circuit goes through, along which the virtual circuit goes through. Now, for this particular virtual circuit, didn't we choose the path first? So the first step is to choose a path from host 1 to host 2, because this was our request. Host 1 is requesting to establish a connection / virtual circuit from host 1 to host 2. So we choose a path first. And in this part of the video, in this part of the lecture, we are skipping the details of how this path is chosen because this is a separate topic. So we have chosen the path, and this path in this example here goes from host 1 to A to C to E to F, and then to host 2. Again, each one, this path goes through routers A, C, E, and F. So each one of these 4 routers will get a table entry that identifies the router as being part of this virtual circuit. But for this to be done, we have to assign a virtual circuit identifier. Do you see these numbers? Number 1 here on this link, and number 1 on this link, number 1 on this link, number 1 on this link, and number 1 on this final link on the LAN. These are the virtual circuit identifiers that are assumed to be chosen for this red virtual circuit. Simply, it's assumed here in this example is that this is the first ever virtual circuit to be established in the network, and number 1 is available. That identifier, connection identifiers or virtual circuit identifiers, VCI in short, VCI, virtual circuit identifier, they just need to be numbers, right? And as long as a number is not used by any other virtual circuit, it can be used, right? So we assume here that this is the first connection to be established, and this identifier 1 has not been used, so we just choose it to be used on every link. Again, as I said, let's try to cut the long story short. What is this virtual circuit identifier? It's a number that is assigned to every link along the virtual circuit. This virtual circuit goes from host 1 to A, this link, which needs a connection identifier. From A to C, this link, it needs a connection identifier. From C to E, this link needs a connection identifier. From E to F, this link needs a connection identifier. Finally, from F to host 2, this link also needs a connection identifier. And we are assuming in this example that identifier 1, number 1, is not used by any other virtual circuit, so we can use it. So what is the only restriction in choosing virtual circuit identifiers? We choose virtual circuit identifiers on every individual link along the virtual circuit. These identifiers in general do not have to be the same. They could be different, but the only restriction is that the number used is not being used by any other virtual circuit. Once we talk about the next one, it becomes even more clear. It becomes clearer. Now, so we assume here that number 1 has been chosen on each link. So this link will use connection identifier 1. This link will also use 1. This link will use 1. This link will use 1. And the final link will also use 1. How does this information go into the table? Again, let's focus on A's table here. A's table has 2 components, incoming and outgoing. Incoming device, if this is router A, what is the device before me on the virtual circuit? What's the device before me? It is host number 1. And what is the incoming virtual circuit identifier? What's the virtual circuit identifier used on the link incoming to me? It is number 1 because we have chosen number 1 already. And this is the best thing to assume. Let's choose these virtual circuit identifiers and then they will be reflected in the table. Now, for router A, what is the outgoing device? It is router C. What comes after me? On the connection, on the virtual circuit, on the path, it is router C. And what is the outgoing virtual circuit identifier? It is number 1 as well. So incoming device, host 1, outgoing device C, incoming device again. Host 1, I'm talking about router A or the table at router A. Incoming device, host 1, outgoing device, incoming device, host 1, yes, and outgoing device, router C. That's why you see host 1 here and router C here. What about the incoming virtual circuit identifier and outgoing virtual circuit identifier? In other words, incoming VCI, outgoing VCI. Since we selected VCI1 to be used on this link, this is incoming to router A along the virtual circuit, and this is outgoing to router A. What about router C here? Let's check the table for router C. Now, router C, for router C, what's the device before it on the connection? It is A, so the incoming device is A, and the outgoing device is E. The outgoing device is E. According to the virtual circuit identifiers chosen, what's the incoming VCI to router C? It is 1. It is 1. And the outgoing VCI for router C, it's also 1. So as you have noticed here, did you see this one here? VCI1 or virtual circuit identifier 1. This was the outgoing for router A, which has to be the same as the incoming outgoing for router A, the same as the incoming for router C here, because this is the same link here, and for the link we choose 1 virtual circuit identifier. So this is basically the table entry for the red virtual circuit regarding router C. Now what about router E? On the connection, router E, what is the device before? It is C. What is the device after? It is F. What's the incoming VCI? It is 1. What's the outgoing VCI? It is 1. That's why you see all VCIs being 1 in the first entry of the tables. Of course, router F has also a similar table. Now, let's focus now, before we talk about the next virtual circuit, let's focus on how the routers use this virtual circuit entry, this table entry. How is it being used? Now, so let's go basically to host number 1. Host number 1 wanted to establish a connection or a virtual circuit so that it can start sending packets, right? Now, host number 1 sends the first packet, and this packet goes to A by default. Before sending this packet, by the way, this packet still has a header. This packet still has a header, but as opposed to the connectionless service in which the header must contain the full address of the source and the full address of the destination, as in our regular letters that we are exchanging, right? in connection-oriented services, since the path is fixed, we don't have to include the full source address and the full destination address in the header. It is enough just to include the virtual circuit identifier, just that number 1, so that we identify that the packet that's coming out of host 1 belongs to this virtual circuit, right? So we have a packet coming out from host 1, and this packet has a header, and this header contains the virtual circuit identifier, which is number 1, the VCI of the outgoing for host number 1. Host number 1 knows this identifier, and it is written in the packet header. Now, this packet arrives at router A. What will router A do? Router A will check its table, looking for a match, searching for a match. Router A has just received the packet from host 1, right? And the header of the packet carries identifier 1. So it is looking in the table. If you receive something from host 1 with identifier 1, so this is the incoming, now the outgoing part will tell what A needs to do, right? So that packet came from host 1. It did not come from host 3, right? So basically, it means for router A, it means that this packet belongs to the first entry and not to the second entry. It belongs to the first virtual circuit and not to the second virtual circuit, because this is what we have as a match. If a packet comes from host 1 bearing virtual circuit identifier 1 in the header, then A will have to do this forward to C and keep the identifier as 1 in the header. We are saying this because in general, routers before forwarding a packet are allowed to go to the packet header and change the identifier as needed. And this will happen basically in the next example when we talk about the blue virtual circuit. So a packet, the packet that is coming from host 1 needs to be forwarded to router C, and the identifier will stay as 1 in the packet header. Now, where will this packet go? Obviously, it will go to C. How will C decide what it needs to do? By checking its own table. So router C will look for a match. If you receive something from A with identifier 1, so obviously this is the match, the entry on top, not the entry in the bottom, because the entry in the bottom, yes, it's coming from A, but the identifier is 2, right? So if a packet is coming from A having identifier 1, that's what you need to do. Do you see this second, the outgoing entry? This is what router C needs to do. Forward to E and keep the identifier 1 in the header. Keep the identifier as 1 in the header, right? So router C will forward to E. Now, when E receives the packet, right, what will it do? It will check its table looking for a match or searching for a match. According to this, if a packet comes from C having identifier 1 in the header, so we're talking about this match and not this one, because we don't have identifier 2 in the packet header. We have identifier 1. Then from the other side of the table, router E will know what it has to do. It needs to forward to F and keep the identifier 1 in the packet header. So eventually the packet will arrive at F, and now F will do the last step of sending the packet locally along the local area network, along the LAN, to the final destination. But we understand from these tables, we understand how the packet is going from router to router based on the table entry and based on the virtual circuit identifiers. Now let's go to the following. We will continue with the example. We will not talk about a new example. No, actually, we will continue with the same example. So assume that this virtual circuit is still being used. It is not deleted yet. It is not torn down or anything. It still exists. So that table entry still exists. However, now at some time after establishing the red virtual circuit, host number 3 is requesting to establish a new virtual circuit with host 2 as well. So this is a new sending host, but the final destination host is the same as that destination host for the first virtual circuit. That's okay. This can happen, right? So hosts could be involved in multiple virtual circuits. Routers can also be involved in multiple virtual circuits. So let's go to this case. Now we want to establish a virtual circuit from host 3 until host 2 according to the connection-oriented approach here in the first slide. According to the connection-oriented approach, what is the first step? A path is chosen from the source router to the destination router. So we have to choose a path first. Assume that this is the path that has been chosen, the blue one. So this path goes from host 3 to router A, to router C, to router E, to router F, and then to host 2. So this is really an extreme case. So both virtual circuits almost overlap in the path. So only the first link is different in both virtual circuits, and then after router A, they coincide exactly. They follow exactly the same path. Both virtual circuits follow exactly the same physical path. So the path has been chosen according to some criteria, let's say shortest path, path with maximum available capacity, minimum delay, and so on. A path has been chosen, and this path is shown here in blue. Again, what are the routers on this path? A, C, E, and F. A, C, E, and F. So each one of these routers will need to get a new entry in the table so that the router will understand that it is also involved for the new virtual circuit. So what have you noticed in terms of the table entries? How many table entries do we have? We have a table entry for every connection in the network. For every virtual circuit, we have a table entry. Of course, maybe those tables don't look that large, so maybe these ones look larger in the example. However, this table is complete. This table is complete because in the connectionless case, the table contains every possible destination and we have them all. But in the connection-oriented case, the table has every possible connection, and here we are assuming only 2 connections. If we get more connections, the table will grow. As a matter of fact, the tables in connection-oriented can grow much larger because the table contains every possible connection. A connection in real life, a connection means a host that starts a conversation with another host, a host that starts a connection with another host, and this corresponds to a network user. Let's say I start browsing the internet. I'm getting connected with basically a web host, a web server. So I have a connection between my computer and CNN. As long as we're using connection-oriented services, it means that we're establishing a virtual circuit between my machine and that server, right? And the CNN server. I'm sending an email. It means we're having a virtual circuit and so on. So whenever we have someone using the network, requesting to establish a connection for the purpose of sending packets, this means we have a newly established virtual circuit, and this goes into the table. So in short, the tables in case of connection-oriented can grow much larger. Another argument is also that the connection here is between 2 devices, from host 1 to host 2. So the virtual circuit or the connection is between a pair of devices, and as you notice mathematically, we have more pairs than routers. If we have 1, 2, 3, 4, 5, 6 routers, how many pairs of routers do we have? 6 times 5, 30 pairs, right? Maybe in the introduction when we talked about how many links we have in a fully connected network, it's exactly the same argument. If we have a network with 6 routers, it means the size of the table in the case of connectionless will have a size basically consisting of 6 rows, of 6 entries. However, if we have the same network of 6 routers, and we simply assume that we have a virtual circuit between every pair, in this case, we will have 30 entries. In short, the tables in connection-oriented can grow much larger because the tables here reflect individual connections. Whenever someone is doing something in the network, like browsing the network, watching a video, sending an email, whatever, getting connected to the bank, going to Amazon to buy something, whenever we have a user, a network user, as long as we're using connection-oriented for everything, it means that we have a new virtual circuit, and this new virtual circuit will be reflected in the table, so these tables can grow much larger. So let's go back to our example. So we have a virtual circuit established between host 3 and host 2, and that virtual circuit follows the path from host 3 to A to C to E to F, and then finally to host 2. Let's choose the virtual circuit identifier so that we can talk about the table entry. This is the first link for the new connection host 3 ACEF H2. That link, is this link being used by the other virtual circuit? No, this is a link and this is another link. So the fact that we're using VCI1 here does not prevent us from using VCI1 here, because this link here, this particular link, is not used by any other connection, right? So number 1 can in principle be used by this virtual circuit. So let's assume that we're using virtual circuit identifier 1. However, for the next link, this link between A and C, is this link being used? Yes, it is part of the red connection and number 1 is being used already. It is reserved. So we have to use another virtual circuit identifier so that we don't confuse between these two virtual circuits. It has to be number 2. And the same follows because we're having the same links. So this link is being used. So we have to use number 2 so that we don't confuse with this number 1 that is being used by the other virtual circuit. This link is also common with the first virtual circuit, so we have to use VCI2. Finally, this link is also common with the first virtual circuit, so we have to use VCI2, right? Again, what is the only restriction? The only restriction in choosing a VCI for the virtual circuit. Again, let's not make a mistake. It is not a VCI for the virtual circuit. We're not choosing a number for the whole virtual circuit. No, for each virtual circuit, we are using a set of numbers. A number per link, a VCI per link. And the only restriction when choosing the numbers is that the number is not used before. This link has no other virtual circuit. We can use number 1. This link has a virtual circuit already, so we have to use another number different from 1. It could be 2, 3, or 4, but in this example, we just assume that we use virtual circuit identifier 2 and in the other links as well. So let's go to the table entries here. In the table entry for router A, again, we have incoming and outgoing. Incoming device, outgoing device. For the new virtual circuit, router A, what is the incoming device? Host 3. And the outgoing is host C, is router C. So for router A, along the new connection, the incoming device is host 3 and the outgoing device is router C. So we have host 3 and router C. What's the incoming VCI? 1, because on this link, incoming to router A, number 1 is being used. And what is the outgoing VCI? 2. On this link, outgoing to A, it is VCI 2. That's why we have 1 and 2 here. Now, once we continue with the other routers, router C, the table entry for the blue connection. What's the incoming device? A. What's the outgoing device? E. That's so easy. A and E. It just comes from the path, right? Router C, before it, we have router A. After it, we have router C. What about the VCIs? We have chosen 2 on this link and 2 on that link. So incoming to C is VCI 2. Outgoing to C, we have also VCI 2. And then at router E, incoming device is C. Outgoing device is F. Incoming VCI is 2. Outgoing VCI is also 2 because 2 is used on the link incoming to E. And 2 VCI 2 is also used on the link outgoing to E. That's why we have 2 and 2. Now let's follow a packet. Once we finish that, it means that we have covered this idea and we can talk about the next example. Now let's follow a packet. Host 3 now sends a packet that belongs to this connection. The packet wants to go to host 2, right? The packet wants to go to host 2. Host 3 knows what is the outgoing VCI, so it will create a packet, and in the packet header, it will put VCI 1 because this is the first VCI used. That's the outgoing VCI if we talk about host 3. So incoming VCI for router A is the same as the outgoing VCI for host 3 itself. So we have a packet that is being generated here, and this packet will contain in its header VCI number 1. Where is this packet going? Obviously, this packet will go to router A because host 3 is connected to router A. So router A will receive a packet. Where is this packet coming from? It's coming from host 3. What is the VCI of this packet? In the header, it is VCI 1. Now let's look for a match. Is this coming from host 1? No, it's coming from host 3. And the VCI is 1 in the header, so this is the match. So from the other side of the table, router A will know what it has to do. Send to C and change the VCI into 2 in the packet header before forwarding the packet. Rewrite basically the VCI value which is written in the header. Change it from 1 to 2 and then forward. That's what this table entry says. Forward to C and change the VCI in the header to 2. Now forward the packet. So this packet is forwarded to C. So who will receive the packet? Router C. What is the VCI written in the packet header? 2, because it was changed by router A. So C, when C receives that packet, it will search in its table for a match. Now C has just received the packet that comes from A, bearing VCI number 2, not 1, bearing VCI number 2 in the header. So the match is in the second entry, and this is what I have to do. Forward to E and keep the VCI as 2. No need to change because the next VCI is also 2. So the packet will be forwarded to E. What will E do? E will also consult its table, searching for a match. Router E has just received the packet coming from C, and that packet has VCI 2 in the header, so the match is the second entry and not the first one. And from the other side of the table, I will understand what I have to do. I have to forward to F. However, when I forward, I can keep the VCI as 2. The VCI is not changing here, so I will send the packet to F. F will do something similar using its own table. Eventually, the packet will arrive at host number 2. So this basically finishes the story. This finishes basically tracing of a packet from its source to its destination along a virtual circuit, and we understand also the structure of the table. Now, this is an alternative example. It's a smaller example that will clarify basically more. It will just emphasize more. It will elaborate more on how the routing tables look like in case of virtual circuits and how we have to choose the VCIs to avoid conflicts. So here in this network, assume that we have router 1 and router 2. So we have 2 routers in the network connected by a link, and then router 1 is connected to 2 hosts, host 1 and host 2. Router 2 is connected to 2 other hosts, host 3 and host 4. We need to establish 2 virtual circuits in order. So first, we have to establish a virtual circuit from host 1 to host 3, from host 1 to host 3. And then before removing this connection, we have to establish a second virtual circuit from host 2 to host 4. Now, the graph that you see in front of you here is really a special graph. It has no cycles. So as opposed to this kind of graph in which we have different alternative paths. So from host 1 to host 2, we have assumed, so it was given to us in this example, assumed that this is the path. But is this the only path? No. We could have chosen also like this, right? Or even like that, and so on. So we have different alternative paths simply because the network has cycles here. The network has cycles, so if you fix a source, you fix a destination, we could have different alternative paths from source to destination. So we have to assume that according to some criterion, we choose a good path or an optimal path, right? Here in this specific simple example here, we have no cycles. And this special graph with no cycles, by the way, is called a tree. So if you see a graph like this, it is called a tree, and one of the characteristics of trees is that there is only one possible path from host 1 to host 3, which is this. There is no other alternative path. So the path chosen for the first virtual circuit is host 1, R1, R2, host 3. So host 1, router 2, and then host 3. Now, let's postpone this until we talk about the table entries for the first virtual circuit. It is the red one here. So the red path. Let's choose virtual circuit identifiers along each one of the links, right? Since we assume that this is the first path established, identifier 1 is available. So that number 1 as a numeric value is available to be used as a connection identifier or as a virtual circuit identifier. So we choose number 1 on this link, number 1 on the second link, and number 1 on the last link as well. Let's talk about the table entries. Now, each one of the 2 routers, router 1 and router 2, because they are part of the virtual circuit, they are part of the virtual circuit. So each one of them, R1 and R2, will get a table entry that identifies them as being part of this virtual circuit. So router 1, let's look at the table for router 1. Incoming component, outgoing component. In more detail, incoming device, incoming VCI, incoming virtual circuit identifier. Outgoing device, outgoing VCI. Let's look at that table entry. For router 1, what is the incoming device along the connection? Host 1 is the incoming device. What's the outgoing device? Router 2 is the outgoing device. What's the incoming VCI? 1. And what's the outgoing VCI? It's also 1 because these have been chosen already, right? Okay, let's look at router 2 according to the red connection. What's the incoming device? R1. What's the outgoing device? Host 3. What's the incoming VCI? 1. What's the outgoing VCI? Also 1. So incoming VCI is 1, outgoing VCI is 1. Now, assume that this entry still exists because this virtual circuit is still being used. So host 1 is still injecting packets that need to go to host 3. But at some point, while this connection still exists, host 2 wants to establish a new connection with host 4. So we have a second connection here. in chronological order. We have a second connection, host 2 to host 4, right? What's the first step in establishing a connection? The first step is to choose a path from source to destination. According to this particular figure here, to this particular topology, we have only this path available that goes from host 2 to R1 to R2 to host 4, host 2 to R1 to R2 to host 4. Before we talk about the table entries, let's select the relevant virtual circuit identifiers. For that new connection here in green, for that new connection, it is using this link first. The link from host 2 to R1. Is this particular link being used by the first connection? No, the first connection going this way. So this link is not used, which means in principle we can use identifier 1. That's allowed, right? So let's say we choose identifier 1 so that we get basically a general scenario. We use identifier 1. Now the next link in the virtual circuit, is this link between R1 and R2 being used by the other connection? Yes, it is being used, and VCI1 is reserved already, so we cannot use it. We have to use another one. Let's say we choose identifier 2. Of course, it could have been 3 or 4, but if we simply assume that we have to choose them in order. So first you try identifier 1 if it's available. If it's not available, then go to 2. If it's not available, then go to 3, so that we get a unique solution here. So here we use identifier 2. And on the last link, this last link from R2 to H4, is it being used by the first connection? No, the first connection is going along this link between R2 and H3. So this link is not being used by any other connection in this example. So in principle, it means we can choose identifier 1. So identifier 1 followed by identifier 2, because this link is shared between two different virtual circuits. One of them is using identifier 1 and the other is using identifier 2. Finally, the last link is not common and we can come back to identifier 1. Now let's talk about the next table entry, the green table entry in R1 and R2 that identifies the second virtual circuit or the second connection. In router 1, what is the incoming device? We're talking about the new virtual circuit. The incoming device is host 2. What's the incoming VCI? Number 1, right? Because this is the VCI chosen on that link. What's the outgoing device? R2 is the outgoing device and the outgoing VCI is VCI number 2. So again, R1, incoming device host 2, outgoing device R2, host 2, R2, incoming VCI 1 and outgoing VCI 2. What about R2 here? What about R2? Incoming device R1 and outgoing device host 4, because we're talking about the green connection. Incoming VCI 2, outgoing VCI 1. So R1 incoming device, host 4, outgoing device 2, incoming VCI 1, outgoing VCI. That's how the table would look like. These two table entries represent the two virtual circuits that we have established from host 1 to host 3 and from host 2 to host 4 respectively. Let's wrap up by looking at a general comparison between datagrams and virtual circuits. Datagram again means connectionless and virtual circuit again means connection oriented. Can we compare between the two? Can we say one of them is better in general? That's really hard because usually we have trade-offs in engineering disciplines, in life in general. If you have an advantage, then usually there is a disadvantage or you have to pay the price somehow. So basically we have a variety of comparison aspects. Let's compare basically in terms of these different issues and let's see which one is better. So we will spend some time talking about this table and then we will finish the video. Connectionless and connection oriented. From the issue, from the point of view of circuit setup, establishing the connection. In connectionless, we don't need to establish a connection because packets get injected individually. Different packets can take different paths if those tables change along the way, right? So this is possible and we don't need to establish a connection, right? So establishing a connection or establishing a circuit is not needed. In connectionless, it is required in virtual circuits or in connection oriented. So which one is better? We would say connectionless is better because it has less overhead. I don't have to establish a circuit beforehand, right? From the addressing point of view, what kind of address is written in the packet header? If we're talking about connectionless, we said several times that the packet header needs to carry the full source of the source, I mean the full address of the source and the full address of the destination. But in connectionless, in virtual circuits, we don't have to contain the full source address and the full destination address, because we have virtual circuit identifiers that distinguish between the different connections, right? And it's enough just to include the virtual circuit identifier in the packet header. Usually the virtual circuit identifier is a smaller number. It's not as large in terms of the data size as a full address, right? So this means basically that the packet header in connectionless has to contain the full source and destination address, which is more information in the packet header, versus here in the case of connection oriented, in the case of virtual circuit, the packet header contains only a short virtual circuit identifier. It carries only a short virtual circuit identifier, which means less overhead. Remember, packet headers contain extra control information. So that extra control information in the header is not part of the data. At the end of the day, I'm not interested in sending this information. I just need to add it so that my data can get transmitted, can travel through the network so that it can arrive at the actual intended destination host. So it's overhead. Right? Overhead means using more of the network bandwidth, using more of the available capacity. So who is better from this point of view, from this regards, right? We would say that virtual circuits is better because the packet header contains less overhead. Simply, we don't have to put the full source address and the full destination address. We can replace that by a short virtual circuit identifier. State information. What kind of information needs to be stored in the tables, in the routing tables? In connectionless, what is in the table? We have an entry for every possible destination. But in connection-oriented, what is in the table? We have an entry for every virtual circuit, for every connection, right? For every connection, the router needs to know information about the connection, where it's coming from, where it's going for individual connections, where it's coming from, where it's going, what's the incoming VCI, what's the outgoing VCI, and these tables can grow really large. And this is what we call state information. In connectionless, routers do not have to store any information regarding individual connections. There is, as you see here, the table contains only the possible destinations. There is no information at all about individual connections. Who is sending to who is connected to, there is no information stored here, right? However, in the connection-oriented case, tables have a specific entry. We have a special entry for every connection. So we have state information for every connection being stored in the tables. Again, in connectionless routers do not store state information about individual connections. The tables do not contain anything about individual connections, who is sending to who, but the table here in virtual circuits contains basically information about individual connections. We can also rephrase all this by simply saying that the tables can grow much larger in virtual circuits as opposed to datagrams, and this can be regarded as an advantage for connectionless. Now let's go to the next topic, routing. When is a routing decision made? A routing decision is deciding for the path. In datagrams, in connectionless, we have to make a decision for each packet itself. However, in virtual circuit, we have to do this routing decision. We choose a path at the connection time. So when we establish the connection, we choose a path and then all packets will follow the same path. So basically we can think of this as an advantage for virtual circuits because again, it is less effort. We have to choose the path once at the beginning of the connection and then the path stays fixed. But in datagrams, paths can change from time to time, right? Effect of router failures. Imagine that during the operation, router C fails. What is the effect if we have a connection-oriented service versus a connectionless service, right? In the connectionless service, packets are being routed independently. So if a router crashes and by coincidence a packet was here, the packet will get lost, but future packets may take different paths in the future. So future packets are not affected. However, in a connection-oriented service, if that router fails, it means the whole virtual circuit fails, and it means that all future packets cannot be delivered. So the effect is much stronger. The effect is much stronger in virtual circuits. So who wins? Who wins when we talk about effect of router failures, basically datagram or connectionless wins, because if a router fails, the effect is much smaller. If by chance there was a packet stored in the router that failed, the packet will get lost, but future packets may still be able to be delivered, right? Because future packets are allowed. It is possible that future packets take different paths from the as compared to the previous packets. However, in virtual circuit, all packets are following the same path. So if a router fails, the whole connection fails, and all packets basically cannot be transmitted anymore, cannot be delivered anymore. And if a packet, even further to this, if router C fails here, it's not just one virtual circuit that fails. All virtual circuits that use this will fail. So nothing can be sent anymore between host 1 and host 2, and nothing can be sent anymore between host 3 and host 2 as well. So that's why you see here all virtual circuits that pass through the failed router are terminated immediately. So the effect is stronger basically, and we would say that from this point of view, connectionless is better because they are more fault tolerant. Basically, they are more agile. Now, quality of service and congestion control are two big topics that we will talk about in future lectures separately. But quickly now, quality of service means what kind of promises can the network make in terms of the quality of service. Quality of service is basically the quality that the network user perceives from the network. In terms of delays, can the network promise that the delays are not too much? In terms of packet losses, can the network promise that packet losses do not exceed a certain limit, and so on? Quality of service. Regardless of the details, we're only asking the following question: connectionless versus connection-oriented. In which case do you think is it easier to make promises about quality of service in terms of delay, packet losses, and so on? I think it's easy to see that it is easier to provide some quality of service guarantees in virtual circuits, simply because the path is established beforehand, and I know the path. I control the path. When I establish future paths, I can make sure that that future path does not interfere with the first one, so that it still guarantees quality of service, right? To make the long story short, in virtual circuits, the paths are known in advance, and if we choose these paths intelligently, we can make some promises about the delays, about the packet losses, and so on. However, in datagrams or in connectionless services, paths are not known in advance. Different packets can take different paths, so it is more difficult, relatively, it is more difficult to promise any guarantees on the quality of service. What about congestion control? Congestion control is simply avoiding congesting some of the network links. So making sure that this link does not get congested with too many packets traveling through it, right? So if we need, again, regardless of the details, because this is a separate topic that we will talk about in future lectures and future videos. The main question is datagrams versus virtual circuits. In which case is it easier to avoid congestion? Again, I think it's clear that it's in the case of virtual circuit or connection oriented, it could be easier to avoid congestion because all paths are known in advance. Everything is under control. I know that this is my path and all packets are following this path. If we have a new connection, I can choose that path intelligently so that we avoid congestion. However, in datagrams or in connectionless services, again, different packets may follow different paths. Things are not under control, and it might be more difficult. It might be more difficult to avoid congestion. So from the point of view of quality of service, guaranteeing some qualities of service, delays, packet losses, etc. And from the point of view of avoiding link congestion, virtual circuit is better. Virtual circuit or connection oriented is better, simply because the paths are chosen beforehand and the path is under control. We know that this is the path that all packets will follow. Thank you. This will finish this video, and we will see you next time with the routing algorithms. Thank you. Assalamu alaikum wa rahmatullah.